converging our GRFs for us. So I have this a few times. It'll play again if it didn't. You caught it. Next slide. So we got a smiling tank tread, and we got our center of gravity way up high, and this thing's going at 7.1 miles an hour, and it's as stable as a table. You can see this thing going by like that. I think I got this one up to 10. I couldn't get the motor to go that fast, so I unhooked the motor, hung it from a string, and let it there, and it didn't jump or bounce. So the stability is independent of the speed, really. You could have a caster like this, and the treadmill could be screaming underneath you. But if you're as stable as a rocking chair riding on that, you don't see the speed. So attitude stability, can't see the speed. The only way to change your speed or accelerate, you have to have friction. Next. So we're going to look at these principles apply no matter what your particular geometry. In any system, you can identify a CG, a metacenter, and some cloud shape of where the contact cloud is going to go, and also shaping of those ground reaction forces, including the friction, to converge to metacenter. When you have a floating sphere, the resultant is always straight up, so you have position control only, but no speed control. So we want to converge those vectors so that we have control of both attitude and acceleration. Next. So there's the vectors, there's the analogy. When we want to get away from, at the speeds we're interested in, is this. And the reason why is just technical. Here we have our cloud of possible ground contact points. And we can look at this and say the instantaneous radius of curvature of the effective cloud in the region of interest near the ground, and all the way around, just in this geometry, is the metacenter, the axle of the effective wheel. The metacenter here is so far below the CG that the CG is outside the metacentric sphere. Terribly unstable. To stabilize this at all, you have to modulate that ground reaction vector with throttle modulation to overcome the geometric instability. So we don't ever want to do that when we want to go to highway speeds. We can't calculate with a microprocessor fast enough to do it at any reasonable size. We'd overwhelm our computers, and we need the bandwidth for other things. It's just to throttle, make the stability dynamic. Next, only got a few more slides. This, you don't see the convergence. Let's move with the robot. Next slide. Same ground reaction forces, we're going to move with the robot. Next, moving with, and I plotted these by measuring from data and plotting at speed, they converge to a high degree of precision. So I can't even see the difference on the lines. The convergence is that tight. Next. So our traditional slip model is one spoke of our wheel. And the ground reaction forces always go right through the metacenter, which is at the CG. So that's neutral stability. You have to control it if you want to control anything, but it'll go steady state for you. Next. Go back one slide. If you're walking slow, yeah, you got that. And once you start running, you got that. But notice these curves are symmetrical, so they're neutrally stable. Next. That's a symmetrical curve. It's a sine. This is your horizontal ground reaction force, slowing you down here, speeding you up. Next. But real running biped systems, to all the precision of all the data I've seen, this is the best graph. Walking, transition to running, it's not symmetrical, and it peaks early. Next. So, in time, we want to peak before the 50% mark of the stride. But that's the way everybody plots it. I want to plot it the other way. So we're running that way, and the ground's going by. Next slide. So I flip it over. The blue is a sine curve symmetrical. We don't want to do that. That's neutral. We don't want to peak late. We want to peak early. And x sine x mapped from this point maps it so precisely from the graphics that I matched it to within less than 1%. It's something like that at steady state. Next. So here we have x sine x ground reaction force peaks early by the CG offset torque conversion to converge to metacenter. Next. That's the picture of the running ostrich in the coordinate system moving with, so you see the convergence. Next. Now, all GRFs are directly radial only to the metacenter by design. Now let's look at what happens if we resolve these into tangential and radial about the hip. Let's look. Okay. We see the radial pointing right at the hip, but early, but not late, we have this torque conversion. So you're paying for ground reaction force to make the things converge in the early part of the stance. By the time we're here, it's almost no torque about the hip, and you're just pushing forward as a strut. And can you throw me the football? Okay, with the running ostrich or any system at this speed, every step, every bound is a Hail Mary. When you throw a spiral, you aim the football, whatever you're doing before, you aim that football up where it's going to go, and you get it spinning, but then you launch it,